All right, this is the 13.7 video. It is on extreme values and saddle points. So extreme values are something that you did before in Calais. Saddle points is a new thing. But there are, just like in Calais, two different kinds of extreme values. There's local extreme values and absolute extreme values. So these would be the local maximin and the absolute maximin that you did in Calais. But here, instead of it being a two-dimensional curve, it's going to be a three-dimensional surface that you're finding maximins for. So because as you can tell, this video is already really long, I just want to point out a few things that I want you to read. And again, you can either pause the video and read them now, or you can come back and look at them later. And then I'll just kind of show you where the stuff is in the book, but I'm going to show it to you in my notes because I worded it maybe a little bit differently and maybe an easier way to see it. So just go through really quickly and show you where everything is in the book, and then we'll switch to my notes. So it starts on page 740, and read these two paragraphs at the top of the page. And then here is the definitions for local maximin. And they tell you here some books will call them relative maximin. So local and relative, they mean the same thing. And so first derivative test is something that you did in Calais. Here the derivative is a little bit different because now it's a function of two variables. And so for the derivative you have the partial derivatives with respect to x and y. And then here's a picture. This picture always reminds me of like ice cream with cherries on the top, but it's a picture of the three-dimensional version of what maxes and mins will look like. And so maxes obviously would be high points. And so before, maxes and mins were higher or lower than the points on either side of them. But now you make this disc and they're higher than all of the points. The word they use is nearby. So higher than all the points nearby, which would be all the points around, all the way around them. And then here they talk about what a critical point is. And so a critical point is either where both the partial with respect to x and the partial with respect to y are 0, or where one or both of them do not exist. Okay, and then here's just a little bit more information about critical points, and then here's the definition for a saddle point. So a saddle point is something you would not have had in 2 dimensions. You're only going to have it in 3 dimensions. And what a saddle point is it's, so like here, if you look at this one, this is maybe a good picture. If you're coming this way, see how the origin is low, right? Because up here you were high and then you came down. So it looks like a min coming from that direction. But if you came from this direction, or the back side, which you can't see, if you came from this direction, then do you see how it's a high point? So it would be a max, but it obviously can't be both. And so the reason why they call it a saddle point is because it comes usually in graphs that look like saddles. And so you can think about a saddle like on a horse, right? If you look at the part where your legs are, then you're going up, and so it would seem like it's a max. But then if you look at the part, like the front and the back of the saddle, then it's low, so it would be like a min. So that's what a saddle point is. Okay, so again, they talk about that more on page 741. And then here they have the second derivative test for local maximin, which is obviously a little bit more complicated than for the Calais version because, oh, here's maybe, if you had trouble seeing the maximins from that other picture, if it was maybe too much going on, you can kind of see it here with the blue. See how on the blue, that would be a min, but on the yellow, that would be a max. That would be a saddle point right there at the origin. So if that's easier to see from that picture. Anyway, what you're going to have here is this thing called the discriminant. And the discriminant is the product of the doubles, xx and yy, on the second derivatives. And then minus the xy squared, because xy is the same as yx. So you could think about this as like here. Well, no, they wrote it that way. Anyway, as like xy and yx, but xy and yx usually are the same thing. And so it's just squaring one of them instead of finding both of them. So we'll look at this test in a minute, but this is the one that we're going to use for local maximin. And then here on page, what page is this? 743, they have for absolute maximin. These are way more complicated than they were in Calais. So if you remember from Calais, you were doing the same kind of steps. You would find the critical numbers, and then you would find the y values at the critical numbers. You would find the endpoints and find the y values at the endpoints, and then you would look through the list and see what was the biggest and what was the smallest. But what's different here is on the boundary, instead of it being an interval, so you just had like, you know, the left number and the right number, and you would just plug in the two endpoints of an interval. Now the boundary is going to be like a square or a triangle or a circle or something else, and so it's a lot more complicated. Okay, so we'll look at that in a minute. And then here they have just kind of a summary of everything all right here together, which is nice, and some of the limitations about the Theorem 11. So I'm going to switch over now to my notes. I think it's maybe a little bit easier to look at it here because I kind of have it broken down without all the extra words. Okay, so this is the same idea from calculus. In calculus, I don't know if you remember this from Calais, but in Calais, the critical numbers, those were all the possible candidates for the maxes and mins, but just because it was a critical number didn't mean it was going to lead to a max or a min, so it's the same thing here. But if you know there's a max or a min, then you could say that the partial derivatives would have been 0 there. But just because the partial derivatives are 0 does not mean there's a max or min. So it only works in one direction. It's an if-then statement, not an if and only if. And so here would be the reverse. If the partial derivatives are 0, then you maybe do, or you maybe don't have a local max or min. So again, it doesn't work in both directions. It does work in this direction. If there's a max or min there, then you know that the first partial derivatives are 0. If the first partial derivatives are 0, there may or may not be a max or min. Okay, critical point. Critical point would be points that are interior points as opposed to boundary points. So they're on the inside, not on the boundary. And they come from either, and pretty much exclusively for your problems, this first one, where both f sub x and f sub y are 0, or occasionally where either one of them does not exist. Okay, that doesn't happen very often in your problems though. All right, and then a saddle point, this would be, you know, if you have, sometimes it's high and sometimes it's low. Sometimes it's, you know, it would be a max value. Sometimes, oh wait, no. Sometimes it would be a min value. Sometimes it would be a max value. So that would be a saddle point. And again, there were some pictures in the book that were helpful for that. And then the second derivative test, this is the one that we're going to actually use. Okay, so I have it written here in maybe an easier to read format. So what you would have would be some critical point AB. So in Cal A, they were critical numbers because they were just X values. In Cal C, they're critical points because they're ordered pairs. So they have to have an X coordinate and a Y coordinate. So it would be, I don't remember what letter they used in Cal A, maybe C or something, where C was a critical number, but now it's AB is a critical point. Okay, so it's an order pair. So suppose that f sub x equals 0 and f sub y equals 0 at the point AB. That means that AB is a critical number, and then it may or may not be a max or min. So there's a max at AB if the fxx is negative and the discriminant is positive. Okay, and then there's a min if fxx is positive and the discriminant is positive. Notice on both of these, for the max and the min, for both the max and the min, the discriminant is positive. So that's the first thing that you're going to check is the discriminant. If the discriminant is positive, it's either a max or a min, and then you check the fxx, the sign, to determine whether it's a max or a min. And so this may seem backwards that the negative goes with the max and the positive goes with the min, but it makes sense if you think about second derivative stuff from Calais, the critical, concavity, right? So if it was, hold on, open my pen. Okay, if it was concave up, the second derivative was positive. If it was concave up, but then a point would be low, so it would be a min. Or if it was concave down, the second derivative was negative, if it's concave down, but then the point would be high, so it's a max. So because these are second derivatives, if you think about them in terms of concavity, then it makes more sense. All right, so next, number 3. If the discriminant is negative, then it would be a saddle point. So again, if the discriminant is positive, it's either a max or a min. If the discriminant is negative, it's a saddle point. If the discriminant equals 0, then you can't use the second derivative test and you have to do something else. I don't think that ever happens in any of your problems though. All right, so speaking of the discriminant, again, it's, and you don't have to do it this way. This is just, if you're bad at memorizing, kind of another way to think about it. This one could, well, either one, could be fyx, because for the problems that we're going to be doing, the fyx and the fxy are the same. So that's why you just do one of them and square it. So it's the doubles times each other minus the mixed one squared. Okay, and then again for absolute max and min, this is the conditions that have to be met for you to guarantee there is an absolute max and min. Your function has to be continuous. It used to be on a closed interval, but now it's a closed and bounded region. So remember, I don't remember what section it was in, but when we were talking about closed and bounded, closed means that it includes its boundary points, and bounded means that you could draw a disk of a fixed radius around it and contain the whole thing. So for you to have absolute max and mins, it has to be closed and bounded. And then these would be the steps. So you're going to list all the critical points and plug them into your function, list all the boundary points and plug them into your function, compare the z values and find the biggest and smallest. Okay. And then again, the summary on page 745. So that's all the stuff from this section. So we're going to look now at some problems. First one is number 2. So the directions, this is page 745, say find all the local max, local min, and saddle points of the function. So when you're doing local max and min, you're going to use here this second derivative test. Okay, that's for local max and min. For local max and min, it's a different method than for absolute max and min, so make sure to know when to do which method. Okay, they don't overlap, except for in that you need to find the critical numbers or critical points for both of them, but other than that, they're not the same. So second derivative test is what we're doing. Here's my function. So I'm going to start by taking my derivatives. Then my critical points are going to come either from where they're both equal to 0 or where either one of them is undefined. But since they're polynomials, they're never undefined, so I'm not getting any critical points from there. So I want to see where they're equal to 0. So I take f sub x, which is here, set it equal to 0, f sub y, which is here, and set it equal to 0. And then now notice this becomes a system of equations, and so you're going to solve it as a linear system of equations. You can choose elimination, you can choose substitution if you want to, you can choose matrices, however you want to solve the system of equations, totally up to you. I like elimination, so that's what I do. So if you look here with elimination, I took this one and I just copied it down exactly like it was, but I rearranged it because I like my variables to be alphabetical. And then this one, to make my x's canceled, I multiplied it by 5, and so it came down here. So if you kind of follow the arrows, you can see where the pieces went. And then notice that because I'm using elimination, I've eliminated my x's, and then I'm able to solve for y. And then when I get the y, I can plug it back into either equation. It doesn't matter. I went with the bottom one, but either one would have worked. Plug it in for y, and then that gives me my x. So notice this is an ordered pair. You have x and y, and that's going to be the critical point. Okay. So moving up here, the only critical point is 2/3, 4/3. So if I have a max or min, it's going to be there, but that could also be a saddle point. So I don't know. So I'm going to use the second derivative test to see. So for the second derivative test, you need the second derivatives. So if you look at your first derivatives, you're taking the derivative of this with respect to x, this with respect to y, and then here, this one with respect to y, which would be the same as doing this one with respect to x, either way. All right, so here's my second derivatives. And then here's my discriminant. This is the formula for my discriminant. So I'm going to plug in the 3 pieces where they go, and I see that my discriminant is positive. So if I look at my second derivative test, if the discriminant is positive, it's either max or min, and so it depends on the sign of fxx, which, I don't know if you noticed this, but well, of course you haven't noticed this. This is the first example we did. You will notice this as we do more examples, that fxx and fyy are always going to have the same sign on these problems. And so it really doesn't matter that you remember whether it's xx or yy. Just remember that it's one of the double ones, because they're going to always have the same sign as each other. So see how here they're both negative? Okay, so fxx is -10, which is obviously negative. So this is a local max. Now you want to find the max value. This is the location, like where it occurs, but the max value would be the corresponding z value. So to get that, you're going to plug this point into my, where is it? Hold on. Here it is, into my original function. So I'm going to plug it in here. So I hope you like fractions. And there's my problem. All that work and you get 0. So plugging in to the original, that'll give you the z value. Okay, and that's the location, and that's the max value. All right, so that's example number 1 of local max and min. We're going to try another one. So if you want to, hold on. Yeah, try this one by yourself. This one's the same in that it's linear. Some of them get a little more complicated, so I'll walk you through those. But go ahead and pause the video and try this one by yourself. All right, so hopefully you did pause the video and try this by yourself. Again, you're going to get a lot more out of these videos if you work these examples with me instead of just watching. All right, so again, you find the first partial derivatives. Again, they're polynomials, so they're never undefined. So your critical points are going to come from where they are both equal to 0. So you set them both equal to 0, and you can use substitution or elimination. Just for a change of pace here, I actually use substitution. So on this one, I solved it for x. It goes this way, it goes this way. And then once I get what x is, I'm going to substitute it in here. So this is substitution. And that gave me this equation, which is just y's. And so I get y is 1. And then I go back up here. And so if x equals 2y and y equals 1, x must be 2. So that's my critical point, okay, 2, 1. You could have done that with elimination and that you would have gotten the same thing. It doesn't matter. All right, so second derivative test, I need my second derivatives. And so here are my second derivatives. Plug it into the discriminant. It's negative, which means that it's a saddle point. So 2, 1 is a saddle point. Okay. All right, so hopefully these are making sense. Those are some of the easy ones. Let's look at some that are slightly more complicated. This is number 14, same, hold on. I think it's the same directions. Let me check before I lie to you. Yes, same directions. Okay, first derivatives. Again, they're polynomials. Again, those are never undefined. Again, I'm going to set them both equal to 0. Here you could not use elimination because notice you don't have like terms for your x's or your y's. So elimination would not work here. It would work if it's linear, but it doesn't work if they're not like terms. So here you would have to do substitution. So if I solve, and it doesn't matter which one, but you could use either equation, solve this one for y or this one for x. So I solve this one for y, and then I plug it into this one. And so I get this, okay, this is equal to 0. So I do greatest common factor factoring, pull out the 3x, and then I can set each of these two pieces equal to 0. So this gives me x is 0, this gives me x is negative 1. It's okay to have a negative under a radical as long as it's odd. So that was okay. And then going back up here, I know what y is. Y is negative x squared, so I can plug that in. Whoops, that one first. Okay, plug that one in, and then I get y equals 0 corresponds to x equals 0. Y equals negative 1 corresponds to x equals negative 1. So this one has 2 critical points. So when you get more than one critical point, you have to test them separately. Okay, but you're still going to start with finding the second derivatives. So I found my 3 second derivatives. And notice before, on the other ones, because my, hold on, let me show you. Yeah, so I'll just show you with number 2. Because my first derivatives were linear, then that made my second derivatives be constants. And so there was nowhere to plug in for the x and y. But on this one, my first derivatives were not linear. And so my second derivatives are not going to be constants. And so they're going to have variables. And so what you're going to do is you're going to plug in the critical points into them and then find the corresponding derivative. And you can do, hold on, let me show you another way you could have done this. And usually this is better. I don't know why I did it that way in my notes. Let me show you just another way real quick. Hold on, write this down. My stupid dog is barking again. I don't know what her problem is. Okay, so fxx is 6x, fyy 6y, fxy 3. So this would be 36xy minus 9. And so you could take this, which is the discriminant. I think the book uses capital D. I may be wrong. You could take this, and then you could plug these points into this. That's another way to do it. Okay, I don't know why I did it this way in my notes, but whatever. They both work. So I plugged in 0 to each of the second derivatives. I plugged in negative 1 into each of the second derivatives. And then I found my discriminants. So at 0, 0, I got negative 9, which obviously is negative. So that would be a saddle point. And then at negative 1, I got 27, which is positive. So it's either a max or a min. So I got to look at the sign of my second derivative. And that was negative. And so if it's negative, that's a max. And again, that's the location. Now for the saddle points, all you ever care about is the location. You don't care about the value. So you're never going to plug a saddle point in. But for the local max, you do want the value. So notice on the saddle point, I'm just giving you the location. I'm just telling you where it is. I don't care what the value is. But for the local max, I need to plug it into my original function to get the value. Okay. All right, so that's that one. So this one's slightly more complicated. I'm going to let you try this one on your own, though. I'm going to yell at my dog. Hold on, I'll cover up the microphone before I do that. So number 18, pause the video and try this one by yourself. Avi, hush! Stupid dog. Okay, sorry. Now my headphones are falling off. Hold on, gotta set this down. Okay, sorry, that was probably uncomfortably loud for you. But at least my dog shut up, so that was good. Okay, I hope you already paused the video and tried this on your own. Now we're going to look at it together. Here's my derivatives. Again, they're polynomials, never undefined, so I'm going to set them equal to 0. But notice on this one, when you set the first one equal to 0, and I'm sure you already noticed this if you tried this yourself, when you set the first one equal to 0, it's just x's. And so if it's just x's, you can solve for it. And so you can go ahead and solve and get the x's. And then if it's just y's, like this one is just y's, you can go ahead and solve for it. And then you get the y's, okay? And so for your critical points, the only time you would pair them up like I'm about to tell you is if it happened like this where you solved them separately from each other. If you solve them separately from each other and they exist kind of in isolation from each other, then you would take this x and pair it with both y's, and you would take this x and you would pair it with both y's. But again, the only time you would do that where you pair it with everything is if you were able to solve them separately. So if you look at all my previous ones, well, there were just one. But like this one. So this one I got 0 and -1 for the x, and then for my y's I got 0 and -1. But I had to keep them paired up with the ones they went with. Notice I didn't do 0 with 0 and 0 with -1, and I didn't do -1 with 0 and -1 with -1. So that was because I solved those together. So if you solve them together, they have to stay together. Okay, so that's the difference. That's how you can tell when they need to stay together or when you match them up like this. If you solve them together, they stay together. If you solve them separately, you have to make every possible combination. So here I end up with 4 critical points. So I find my second derivative, or derivatives, find my second derivatives. And then, again, I did it this way. I don't know why I did it this way. Again, this would be smarter. Let me show you over here. Apparently I wasn't thinking when I was making my notes. I must have been tired. Or my dog was driving me crazy. That's a possibility. Okay, so fxx is 12x minus 18. Fyy, 12y plus 6. Fxy, 0. And so here you can FOIL. I don't know what that number is. I'm not going to waste time finding it right now, or I don't know what that number is. But anyway, you could find this. And then you can plug in your xy values into this if you want to. This would be the discriminant. So you can do it that way, where you find the discriminant and then plug them in. Or you can do it like I did it, which ends up being this really long mess. So I plugged the I plugged the four critical points into the fxx. Then I plugged the 4 critical points into the fyy. I did not plug them into the fxy because, see, it's always 0. So it's always 0. I didn't have to do anything. And then what I'm going to do is take every combination, or not every combination, every pair together. Like here's fxx and here's fyy. So I do those together minus the 0. I just wrote that so you could see it. And that's positive. So I check the sign of fxx. It's negative, local max. And then I'll just let you look at these. You can pause the video and look at those real quick for the other 4. Now, for the 2 that are saddle points, again, don't find the z value. You don't need the z value for the saddle points. But for these 2 that were maxes and mins, you do need the z value. So you're going to plug that into the original function and get the z value. And so for the saddle points, again, just the location, local max and min, the location, and the value. All right, so that's that one. So that's all of my examples for local max and min. I hope that makes sense. There's examples in the book if you need them. But now we're going to move on to absolute max and min. So this is page 746, and the directions say find the absolute max and min of the functions on the given domains. All right, so we're going to look at 32. 32, here's my, I don't know why they call it capital D. That's a little bit confusing because they're using capital D for the discriminant. So I pretend like that's a f. This is just the function. The capital D here does not mean anything related to the discriminant. So they tell you that the region is the closed triangle in the first quadrant bounded by these lines. Okay, so it looks like this. This is the closed triangular region. So for the absolute max and min, you're looking at 2 different things. You're looking at the stuff inside the triangle. That will be the interior. And then you're looking at the boundary of the triangle, and that would be those three lines. Ignore that red dot for right now. I'll show you what that means in a minute. So again, those steps are on page 743. You start with the interior. And that would be the inside. That's where the critical points come into play. So you're going to find the critical points. This part is just like the local max and min. This is the only part that they overlap each other in finding the critical points. So again, I don't know why they're using the D here, but you can pretend like that's an F if that bothers you. So here would be the derivatives. Set it equal to 0. Here I used elimination again just because I like it. So when I solve using elimination, I get 0, 0. But so 0, 0 is the critical point. However, and here's where the red dot comes in. If you get a critical point on the absolute max and mins, you have to check and make sure it's actually an interior point. Sometimes like I could have gotten, I don't know, 4, 1, right? So if I would have gotten 4, 1, that would have been here. That's not inside my region. So you always want to draw your region and shade it so you know what you're looking for. And then when you find your critical point, you want to make sure it's inside the region. So 0, 0 is not inside the region, it's on the boundary of the region, and you take care of the boundary in part 2. Part 1 is the interior. So because it's on the boundary, I know I'm going to get it in part 2. If it would have been something like 4, 1, then I would just ignore it completely because it's not in my region or on the boundary of my region. So here, you did get a critical point, but it's not an interior critical point, so you're going to ignore it. And you'll see it again when we do the boundary. Okay, so that happens a lot. Don't let that bother you. All right, now moving on. This is the fun part. You're going to love this. If you have different colors, if you're a visual person, you might want to pause the video and go grab 4 different colors. It might help you to kind of keep track of what you're doing. You also might want a highlighter or a colored pencil or something. These problems are long, there's a lot going on, and so if you use colors and highlighting and stuff, it makes it a little bit easier to see, especially if you're a visual learner. All right, so here's my same region. So what you have to do, you have to take the boundary and you have to break it down into the separate pieces. In no particular order. This is line 1, line 2, line 3. It doesn't matter which is which. You just have to separate them out. Okay, so you take it one line at a time. So on line 1, all the points, if you look back up here, all the points on line 1, the y value is 4. Okay, so all the points on line 1 have a y value of 4. So you go back to your original function, and in place of your y, you put a 4. So all of your y's are going to become a 4. So it becomes, my y's become 4. Everywhere I have a y, I put a 4. And notice now it becomes a function of just x. So it's a function of a single variable now. And you have to stay between 0 and 4 because if you look up here at the picture, see how the x's stay between 0 and 4? So your x's have to stay between 0 and 4. All right, now that you treat this like f of x, you've got a function, you've got a closed interval. Now it becomes a Calais problem. So I don't remember what section it was in. I'd flip real quick, but then the phone would go all crazy and it'd probably make you sick because it'd be jumping around so much. But somewhere at the beginning of the book, they have absolute maxes and mins. And so once you get it down to here, where you have a function of a single variable on a closed interval, then it becomes a Calais absolute value. I mean, absolute max and min problem. I don't know why I wrote absolute value. It would be absolute max and min problem. Anyway, not absolute value like absolute value bars. That's a little bit confusing. Absolute max and min values, not absolute value bars. Okay, so this is part of line 1, and you're going to do it the Calais way. So you've got to look at the critical numbers and the endpoints. Okay, so for the critical numbers, you take the derivative of this, and notice because it's a function of one variable, it's just a regular derivative, not a partial. So I take the derivative, it's never undefined, so I see where it's equal to 0. And now this is a critical number, because see it's one-dimensional now, critical number. So I plug it in, back up here, plug it in, so x is 2, and I get 13. And so notice here, because the y was 4, that's actually the ordered pair 2, 4, which if you look, would be, here's, whoops, I wrote on that, here's 2, 4, so it would be this point right. Wow, this is hard to look through the camera and, and draw. Takes skills I do not have. That would be that point. See, I just found it right there, 2, 4. So it's on the boundary on line 1. Okay, and this is where you want the highlighter. Highlight these answers as you find them because there's going to be a lot of them, and you've got to go back later and compare them. And so if you highlight them, it makes it easier for you to find them when you have to go back and compare them. Okay, so now the endpoints. This is again the Calais part. On the Calais part, you have the critical numbers and the endpoints. Okay, this is still line 1. So the endpoints were here, the endpoints of the interval. Okay, so my endpoints are 0 and 4. Y is still 4. So I'm plugging them in. Where did you go? Here. I'm plugging them in here. Okay, for x. So plug in 0 for x and I get 17. Plug in 4 for x, I also get 17. There's 2 more values. Go ahead and highlight those so you can find them later. And just to show you, that was this point 4, 4, and this point 0, 4. So see, the critical number gave me the thing in the middle, and then the endpoints gave me the things on the edges. All right, so that's line 1. Now next is line 2, which is this slanted one. So for line 2, if you go back up here, it's not that, you know, like here the y's were always 4, here the x's are always 0. This one, there's nothing that's always the same in terms of x's or y's. Hold on, I have OCD issues, and that's going to bug me that I wrote on that, so I got to fix it real quick because that's just going to drive me nuts every time I look at this picture. So please excuse me for a minute. Okay, that makes me feel happier. So you've got to figure out what this line is. So notice this is the line between 0, 0 and 4, 4. So hopefully you recognize that as the line y equals x. So all the points on line 2 are, line 2, again, that was the line, well, here it is down here, this one, the slanted one, but that's the line y equals x. Okay, so that's where I got this y equals x from. So what you can do is all of your y's are going to become x's. So you replace all the y's with x's. It gets it down to a function of a single variable. Again, your x's are between 0 and 4. So again, that's a Calais problem. So for the Calais problem, you have the 2 parts, the critical numbers and the endpoints. For the critical numbers, you find the derivative. Then you set the derivative equal to 0, and that gives you the critical number. But notice that one also is an endpoint. So really, you don't have, I did it up here because I wasn't paying attention. I went and added this later. I went ahead and did it up here because I didn't pay attention to the fact that it was an endpoint, but I could have ignored it up here because see how it's going to come up here again, so I don't really need it here, but whatever. So I got 0, and so then when I plugged that in, that was 1. So I highlight that and save it. Now I do my endpoints. I already did the 0 up there. I should have saved it and did it down here, but notice I didn't highlight it here because I already have it there. And then same thing here with the endpoint. Notice that on this one, hold on, go back, where are you? Here. The x and the y are the same thing, so that's why I see on these order pairs, they're always like doubles because x and y are the same thing. And so I didn't highlight this one because I already have it right here, and I didn't highlight this one because I already have it right here. So you get a lot of redundancy because what you just got 0, 0, which was there, but then you also got that, whoops, this one, you also got that 4, 4 again. So you already had that 4, 4 from line 1, and so you got it again on line 2. And so notice this 0, 0 that I just got from line 2, I'm going to have it again on line 3. And then same thing here, this 0, 4 that I had on line 1, I'm going to pick it up again on line 3. So you start to have a lot of repeats. Okay, line 3. On line 3 was this vertical one. On that line, all of the x's are 0. Okay, so for line 3, all the x's are 0. You go through and you replace all your x's with 0. It becomes a function of a single variable. Your y's are between 0 and 4. And so that's your boundary here, or your endpoints, excuse me, your endpoints. So you find the critical numbers by taking the derivative set and equal to 0. Again, I got 0, which is also an endpoint. I already had it from up here, so I don't need it again. And then, hold on, turn the page. The endpoints, I already had both of those, so I didn't do them again. So now for comparing the values, you get your values from step 1, which I didn't have any. You get your values from step 2. This is where it's helpful to have them highlighted so you can find them quickly, especially if you're not neat with your work. If you're not neat with your work, you're going to overlook some of these values. So if you highlight them as you find them, it's a lot safer. So you want the biggest z value and you want the smallest z value. So there's a tie for the biggest z value, and then this is the smallest. So the absolute max occurs at the biggest, and the absolute min occurs at the smallest. So notice, just to give you a perspective, of course I do show more work than probably you guys do, but see how that was 1, 2.5 pages? These are long, so don't wait till the last minute to do your homework or to study for the test because they take a long time. So I know you're worried about the actual test, how you're going to have time to do this. The way I can do it is I can go ahead and give you like 1 or 2 of the lines and then just have you do the 3rd or 4th one. So there is a way to make it shorter. Okay, let's look at number 34. This is another one. I'm going to get you started and then I'm going to have you try to finish this one on your own. 34, here's my function. This time it's a rectangle. So it's the rectangle where x is between 0 and 5. Ignore the red dot for right now. X is between 0 and 5, and y is between -3 and 3. So that's my, my region. So I'm going to start with the interior. That would be the interior points on the inside. So find the critical points. And to do that, I do the first partial derivatives, set them equal to 0. Again, I did elimination. So I get y equals -2. Plug that back into either equation, but I did it to the bottom one because it's easier. And then I get 4. So again, when you're doing absolute max and min problems, when you find your critical point, check it and make sure it's actually an interior point. So 4, -2. I go back up here. That's what the red dot is for. 4, -2. That is inside the region, so I can use it as a critical point. If it's outside the region, you can't use it at all. If it's on the edge of the region, you're going to hit it in the boundary points anyway, so you may as well wait till then. But if you used it now, it would be okay. But it would be wrong to use it if it was outside, like somewhere out here. That would not be okay. All right, so for my critical point, it was 4, -2, so I just go back up here to the original function and plug it in to get the z value.